So yeah, this one's about random access in multi-party computation. Now, MPC in general has been doing fairly well over the last decade and a half. Lots of applications have taken off. We have applications in bioinformatics, in data analytics, and whatnot, which is great. However, if you look at, so these are applications where you have two or more parties and they have their own private data. They want to do some computation which combines data from both parties, but they don't want to reveal anything other than the final output. They don't want to reveal any intermediate results. They don't want to reveal their inputs to each other, which is great. But if you look at the slide here, each application is basically a new, you need lots of smart people to spend a lot of time coming up with new optimizations before each of these applications become practical, which is great. We like new papers, but it needs to be easier. So it would be nice if generic methods of developing these sorts of MPC applications were actually practical. Now, if you ask anyone who's ever written MPC applications, the first thing they'll tell you that's really a nagging problem when you write MPC applications is that random access is a problem. So let's say you have a program, and somewhere along the line you make an access. You need to access element 5. Now, the data themselves can be encrypted all you want, but both parties will be able to see you're accessing element 5. And if that 5 somehow depends on the secret data that you didn't want to reveal, if that's an intermediate result that you're revealing. So we don't want to do that. Now, you could, in theory, be able to hide everything by accessing every single element to hide which one you're really interested in. But in that case, you just made one array access a linear time operation. That's a linear scan. That will completely make most non-trivial algorithms completely unscalable. We don't want to do that. The other approach, as the other speakers have spoken so far, talked about so far, is oblivious RAM. Here, the idea is that you take a few elements, you keep shuffling them all the time with every single access, so that when you actually do reveal which element you're accessing, their physical location will not reveal their logical identity. So that works too. They give you access in polylogarithmic time. If you go through the literature, one of the ORAM constructions that we'll be comparing against all the time is the circuit ORAM paper from last year's CCS. It was by Wang Shi and others. So this one is sort of the fastest there is for MPC applications. If you want to hide your access pattern in MPC, this is the best you can do so far. Now, this is great. However, we wanted to sort of see how it plays out in real applications. So if you compare the performance of this existing scheme with just linear scan, if you are accessing every single element, what do you get? It looks kind of like this. So if you have fewer than, say, 10,000 elements or, say, 60,000 elements or so, a linear scan is actually faster. For larger data, this one's good, which is great. However, that's sometimes not quite tractable, because if you look at it, it requires something like 2 seconds per access if you have 2 million data in your array. Which means even if you're trying to just initialize the array, you'll need 2 million seconds. That's several weeks. Just for initializing a structure, just because you want to hide which elements you're interested in, for processing a million data elements, which is not always what you want. So what we wanted to do is to come up with a new construction that will A, have lower initialization cost, which helps, and B, will be able to break even with linear scan at a much smaller size. Now, just to foreshadow our results, if you look at the kind of parameters which work for each construction, here, this graph shows the combination of parameters for which each construction is optimum. So x-axis here is the size of each element, and y-axis is the number of elements. So as you can see, for a large combination of parameters, our approach, even though it's asymptotically poorer, actually helps you. And this is just the access time, without considering initialization cost. So in real application, you will probably want to use our construction, even for some of the red regions. So yeah, for the smaller data sizes, linear scan is still faster. For large enough sizes, you still want to use circuit ORAM. However, when I say large, it means something in the order of several days or weeks, that kind of thing. But for all other applications, you want to use our scheme probably. How do we actually accomplish this? Well, we looked at some of the older schemes, some of the very first earlier schemes by Goldridge and Ostrovsky in '96. They considered this square root scheme. It's really simple, but it was initially considered to be impractical for MPC applications because they require you to securely evaluate hash functions inside a cryptographic protocol. So everyone said that, okay, you know what, this is not going to be tractable for MPC, so that's the one we decide to concentrate on, because why not? So what we do here is that we get around this requirement to evaluate a hash function with every access. And we show that this actually helps. So the rest of the talk, we'll be talking about how our construction applies to a small number of elements, let's say just 4 elements, just for the sake of illustration. And then we'll talk about how it applies to larger sizes, especially how the metadata gets processed. And finally, we'll finish with evaluation and conclusion, right? So for 4 elements, let's say we have an array of just 4 elements. We have wires carrying 4 data elements, and we want to hide which one we're actually interested in. How do we do it? Well, first of all, we start by shuffling it. Through this one slide, we'll be talking about, we'll be using this notation of B. B bytes of data transfer of data will be transferred for accessing one block of item, or operating on one block of item. So for shuffling, we can do it in 5B bytes of data transfer. Once we do the shuffle, next time we want to access something, we can actually reveal which one we're accessing. So in this case, we can reveal that we're accessing the second wire, because we don't know which logical element that really corresponds to it. It's already been shuffled. Now, once we do that, for the second access, however, we need to be a little more careful, because now we need to sort of access 2 elements and secretly choose one of the 2, so that we don't reveal it whether or not it's a repeat. But other than that, we now have to pay 2 B bytes worth of communication. For the third access, we'll have to pay 3 B bytes of communication. And what we do in our construction is that from the 4th access onwards, we'll just reset the whole process. We'll just shuffle again, do 1B, 2B, 3B, shuffle again, 1B, 2B, 3B, and so on and so forth. Now, if you look at the cost here, this is already getting kind of interesting, because we are paying a cost of 11 B bytes for every 3 accesses. This is already better than linear scan. In linear scan, you'd be secretly choosing between 4 elements, 4 B bytes. This is already breaking even for just 4 elements, which is much better than all other ORM schemes. Other ORM schemes, they tend to break even at around 100 or 64, depending on how you count. So over here, it seems like this approach could be promising, even though even though it's a really simple scheme. So what we'll talk about next is how this applies to larger sizes, especially how the metadata gets tracked. So we told you that we're not using a hash function. So what we're doing is using a recursive ORAM. So we'll be talking about how the metadata gets generated and how we keep track of the position map. Okay, so the part that we didn't discuss is that every time we shuffle, we need to produce this extra map that says, you know, element 0 went to position 3, element 1 went to position 0, and so on and so forth. So with every shuffle, we need to do that. And in order to do that, if you just abstract out the problem just for the shuffle, the problem looks kind of like this. So we'll come in with a position, we'll come in with some elements, we'll permute it. While permuting, we also need to produce a map which has sort of the inverse permutation. So if element 0 ended up in position 2, then we need a map that says, okay, 0 maps to position 2, and so on and so forth. Now, for the first shuffle, this is fairly easy. Your inputs are all nicely ordered. You know which ones got, at least the protocol knows which ones got swapped and which one it didn't get swapped. You can just run it in reverse and produce the inverse permutation, which is easy. The second time, it's a little more difficult, because now which element ended up where depends on 2 shuffles instead of 1. You have to combine combine information from 2 shuffles. You don't necessarily want to do that. So what we need to do is come up with some sort of a 2-party protocol that starts with the encrypted representation of where each element is, and we need to find the inverse permutation without telling either party finding out what the permutation is. So we start with the permutation P, and we'll need to come up with P inverse. So we have Alice and Bob, our crypto characters, and the way we do it is that we have Alice pick a random permutation, pi A, and use that to permute the actual sensitive permutation. Once it's been permuted, it gets revealed to Bob. Now, they both see a random permutation. They don't see the sensitive permutation. At this point, what Bob can do is that Bob can locally compute the inverse of the whole thing and combine them back together so that pi a gets canceled out. So you're just left with p prime, p inverse, which is what we wanted. So in this way, we can compute, the two parties can collaboratively compute the permutation inverse without having to reveal the information to each other and without using expensive sorting operations. So yeah, the whole process looks like this. Our ORAM, you start with shuffling, you produce a position map, you make T some number of accesses, you go back, shuffle again, make position map, you do some number of accesses, so on and so forth. You do, for each shuffle, you do square root n log n accesses, so you pay a average cost of square root n log n per access. That's the amortized cost. So next we have the evaluation slides. On the x-axis, we have the data number of data elements, the y-axis time. As you can see, our approach is asymptotically inferior, as we said. So per access time, eventually for large data sizes, we do perform worse. But that's OK, because what this graph doesn't show you is the startup initialization cost, that week-long cost that we talked about. That's not shown here. That's just the per access time. So if you look at the initialization cost, we do about 100x better for pretty much all data sizes. Once again, this means that for pretty much any benchmark where you are spending less than a few days, you probably want to use our scheme. So these are a few sample benchmarks for some data sizes. Binary search that actually counts the initialization cost, whereas previously, oftentimes, other papers would not. And for most of the cases, ours is actually better. And for stable matching, this is just a naive Wikipedia implementation of stable matching. If you want to do custom algorithms, you can definitely do much better. In fact, if you hang around for the poster session, I believe Jack Dorner will actually be presenting a much faster, like 40x faster algorithm. So yeah, we can definitely do much better than that. And script was just a hash function that does lots of unpredictable random access, so we went with that. So yeah, to conclude, we revisited an old scheme, check that whether or not we can do something useful with that. And it turns out that if you're in real life applications, often the concrete costs matter, not just the asymptotic costs. Often your initialization costs, cutoff costs, break-even points, those things are parameters that you need to pay attention to. And hopefully this will make other applications more interesting. So yeah, with that, I'll take any questions.
Hi, thanks a lot for your talk. So I think the original square root ORAM, you can apply it recursively, right? I think it's called hierarchical ORAM.
Yes, that's true.
So can you do that here? And is there any point to doing it?
Yes, there is a point to do it. We are trying to do it at the moment. What happens is that you have to be a little bit careful about not accessing the position map multiple times for each outer axis, which creates asymptotic problems. So doing it naively doesn't work, but it's doable. We're working on it. Yeah.
Thanks.
Are you working on other uses for square root ORAM in heretofore besides multi-party computation?
Pretty much anywhere where, well, the only thing about multi-party computation is that it's slow. So in other cases where you have smaller data sizes, basically, where are interesting, yeah, it's definitely worth looking into.